The first method we can use to solve truss-type problems is called the method of joints. And this is especially useful if we are interested in finding the forces in every member of our truss. The first thing we need to know before we use either method of solving our truss is knowing, can we solve for all of the external reactions in the truss? So really what we want to know is our truss statically determinant? Meaning that it has 3 or fewer support reactions. So this would come if our truss is pinned and has a roller attached to the ground, or perhaps it has 2 rollers attached to the ground. We are looking for these external supports and what form they are in. So if we look at those and there are 3 or fewer, that means that from this external picture, we are going to be able to solve for all of those external or support reactions. Because in this external picture, we know we're going to be able to get 3 equilibrium equations to solve for those 3 unknowns. Now it could come up that if we have, for example, 2 pin connections to the ground, well, that's going to introduce 4 support reactions, 2 x components, 2 y components, making it statically indeterminate, which we'll talk about next. So looking at the external picture, how many support reactions do we have? If it's statically determinate, we'll go down this pathway. The first thing we're going to do, whether it's method of joints or later talking about the method of sections, is construct this external free body diagram, which is going to be a 2D rigid body problem. And we'll use that diagram to solve for these support reactions because we already know that we should be able to develop a solvable system. So the first 2 steps of this truss problem here is really solving it like we did in the previous section. It's just a 2D rigid body and we want to know what the supports are. So the third step, that's going to be the new step, now talking about trusses and specifically the method of joints. What we want to do is go to every pin connection between members and construct a free body diagram. And each one of these free body diagrams is going to be a 2D particle equilibrium problem. So at each pin connection, we're going to center that pin as our particle of interest in the particle equilibrium problem. Then we need to model what every member that's attached to it is doing to that pin. For consistency and to make it easier, I'm going to recommend that always assume that every member it's attached to is in tension. That is to say that every member would be pulling on the pin in that free body diagram. Also for consistency, I recommend using an alphabetical naming convention. Typically, the different points are going to be labeled, for example, A, B, C, and D, and we might name the tension or more generally the force in any member as, let's say, FAB if it's attached to point A and point B, or FBC if it's attached to point B and point C. So if we always name it using an alphabetic naming convention, so for example, the beam between B and C, we say that the force of it is always FBC and never FCB, it's going to be less likely that we are accidentally double counting variables. What we could encounter is in one picture we name the force FBC and we draw another free body diagram and we have the same member but we call the force in that member FCB. It's the same force but it has 2 different names. By always doing it in alphabetical order, it's going to be tougher to accidentally double count any of these forces. So from step 2, we are going to know the proper direction and magnitude of all of those external reaction forces. When we draw these internal free body diagrams of each pin, if an external force appears in it, I'm going to recommend that in the new pictures you do draw the forces that we now know the proper direction of in that proper direction. Note, this is not talking about the members in the structure. We are always assuming tension, even if we figure out that something is in compression or several are in compression, we are still always going to assume tension in the drawings, and we use those FBDs to derive our equilibrium equations. Never redraw these internal forces in the members. The only thing you should draw in the proper direction, once we know the proper direction, is the external forces from steps 1 and 2. Once we have the free body diagrams of the particles or the pins that we want, now we're going to be able to solve for the forces in these members. We're going to get 2 equilibrium equations out of every pin diagram that we drew. Because they're particles, we can only sum forces in 2 directions, typically x and y. In these particle equilibrium problems, we can't take the moment as all the forces are concurrent. When writing the equilibrium equations, always use variable names for all of the unknown forces in the members. Even once we start solving for some numerically, always keep it in the variable form and then later substitute in the values once we know them. Once we start solving for the forces in the members, now we can start to make inferences. If we always assume that members are in tension, pulling on the pins, then we can say that a positive value is going to confirm our assumption of tension, and indeed, that member will be in tension. When we get a negative number, that's going to say that our assumption was incorrect. Actually, it was in compression. If we discover that members are in compression, never redraw free body diagrams with arrows pointing in the opposite directions just because that we learned one was in compression. If we're going to be incorrect, we need to be consistently incorrect in all of the pictures. So we're going to let the math work itself out. If the structure is statically determinant and we drew that external free body diagram, typically we are going to have one extra free body diagram we could draw, but we're not going to need. So typically we're going to have one extra pin FBD we could draw, but by the time we need to draw it, all of the unknowns will be solved for. That pin still must be in static equilibrium, and it can serve as a good check to make sure that we did all of the math correctly, that all of our equations were written correctly. However, it's not going to add any new linearly independent equations to the set that we already have. Alternatively, when we look at the external picture, all the way back at that first step, we might see that it's statically indeterminate. We have more than 3 support reactions. Again, if we have 2 external pin connections, this would come up. So we know that we will not be able to solve for all of those external support reactions from just that external free body diagram because we can only get 3 equations and we know that we have at least 4 unknowns. So in the case where we have a statically indeterminate truss, I'm going to recommend we skip even drawing that external free body diagram. We know it's not going to give us enough equations to solve for the unknowns anyway, so we're going to skip ahead and start constructing free body diagrams for the pins. And in the order we want to draw these pins, don't first draw them where the external supports are. Draw them first for internal pins where it's only connected to other members. This is going to make the algebra a little bit easier as we go forward. And ideally, if we have a pin that's connected to only 2 members, that's a great place to start because we know that that pin free body diagram will give us 2 equilibrium equations and we'll be able to solve right away for 2 of those unknowns. Then we can proceed to draw more pin diagrams and keep solving for the unknowns as we go. From the free body diagrams and then the equilibrium equations, we can start to solve for the forces in the members. And eventually we're going to get to the point where we have enough linearly independent equations for all of the unknowns that we've introduced. Those unknowns being the forces in the members. So like I said, for either method, when we start drawing the pin diagrams, if there are pins connected to only 2 members, that's a good place to start. The order does not really matter though, as long as we count enough linearly independent equations for all of the unknowns in those equations. As we get to large trusses, just be aware that we could start to get a lot of equations going if we have a lot of pins, because each pin is going to give us 2 equations. So in a system with 10 pins in it, we're going to possibly get 20 equations just from the free body diagrams of the pins, plus 3 equations if we have the external picture. So it's a good idea to number your equations as you go to make it an easier assessment if we have enough equations for all of the unknowns that we've introduced.